Ligands will be considered as point charges in case of anions, which is negatively charged, or dipoles in neutral molecules. The two options are: if delta naught is less than pairing energy, the fourth electron enters one of the EG orbitals, giving the configuration T2G, 3EG1. For this reaction, the greater the value of stability constant, the greater is the proportion of metal ligand complex in the solution. This point is very much important. Hello everyone, this is Harshita Bhavasar from Vidhyaashram PU College Temple of Excellence. Today, I am going to start session 3 from the chapter Coordination Compounds. In the previous session, we have discussed about isomerism in coordination compounds, Werner's theory of coordination compounds, limitations of Werner's theory, valence bond theory and applications of valence bond theory. In the current session, we will discuss about magnetic properties of coordination compound, limitations of VBT, crystal field theory, electrons in the d orbitals of metal ion in octahedral coordination compounds, color in coordination compounds, bonding in metal carbonyls, stability of coordination compounds and applications of coordination compound. Yes, it's a huge session but very much important and which will give the link between one and another topic. So, I am doing at one stretch. Okay. First, magnetic properties of coordination compound. The magnetic properties of a coordination compound will provide an indirect evidence for the orbital energy which has been involved in the bonding. Okay. And if compounds containing unpaired electrons, then that unpaired electrons will show the magnetic moment and that magnetism will call it as paramagnetic moment. And if the compound containing no unpaired electrons, means absence of unpaired electrons are present, that magnetic moment will not be exhibited. That kind of magnetism will call it as diamagnetic in nature. Okay. And if the unpaired electrons are present, then magnetic moment should be calculated by using Bohr magneton, and that formula is root n into n plus 2. Small n is number of unpaired electrons. This is the very introduction part of magnetic properties. You know already about it, but we have to amplify this concept with the d block elements. The magnetic moment of coordination compounds can be measured by the magnetic susceptibility experiments. The results can be used to obtain information about the structures adopted by metal complexes. For metal ion with up to 3 electrons in the d orbitals like titanium, vanadium, chromium, which is d1, d2, d3 respectively, have 2 vacant d orbitals are available for the octahedral hybridization with 4s and 4p orbitals. In the d block elements, d1, d2, d3 like titanium, vanadium and chromium are having 2 vacant d orbitals to get hybridized with 4s and 4p orbitals to form octahedral complexes. Okay. See here, it is having 2 vacant spaces till chromium. It may relate or hybrid with 4s and 4p to form octahedral complexes. The magnetic behavior of these free ions and their coordination entities is similar irrespective of the strength of the ligand. What are the magnetic behavior of the free ions? In their coordination entities are there. Those are all similar and irrespective of their strength of the ligand. When more than 3 3D electrons are present, the required pair of 3D orbitals for octahedral hybridization is not directly available as a consequence of Hund's rule. Means if there is more than 3D orbitals are present, electrons are present, 3D orbitals for octahedral will not be available for the hybridization. So, it is not directly available as a consequence of Hund's rule. Thus, D4, D5, D6 like chromium, manganese and iron and carbonate cases, cobalt cases, a vacant pair of d orbitals results only by pairing of 3D electrons, which leaves to 1 and 0 unpaired electrons respectively. Okay, see here, okay, which will get pair up with results by the pairing of 3D electrons, which leaves 2, 1, 0 unpaired electrons respectively. See here, 2, 1 and 0. Okay, there is sometimes 2 unpaired electrons, there is only 1 unpaired electron, and there might be no unpaired electrons only after pairing. The magnetic data will agree that because of magnetic spin only, the coordination compounds are going to form with D6 ions, but in D4 and D5 complexes only there are some complications. Okay, limitations of valence bond theory. It has a number of assumptions, does not give quantitative interpretation of magnetic data, it doesn't give any magnetic data, and it has some number of assumptions only, does not explain color shown by complexes, could not predict tetrahedral or square planar shape for the coordination number 4, could not distinguish between strong and weak ligands also. There are number of limitations of valence bond theory and as shown here. Next, crystal field theory. Metal ligand bond is considered to be ionic, which arises purely from the electrostatic interaction between the metal ion and the ligand. When metal ligand interaction is considered as ionic, before that electrostatic interaction has been done between metal and ligand. Ligands are treated as point charges in the case of anions or dipoles in case of neutral molecules. Ligands will be considered as point charges in case of anions, which is negatively charged, or dipoles in neutral molecules. The 5 d orbitals in an isolated gaseous metal atom or ion are degenerate. Means the 5 d orbitals will be isolated gaseous state and it will be considered as degenerate level when they are having same energy levels. Due to the negative fields of the ligands, the degeneracy of the d orbitals is lifted, result in the splitting of the d orbitals. Due to the negative charges or negative fields of the ligands, the degeneracy will be lifted up. The splitting of d orbitals can be seen. Crystal field splitting. The splitting of 5 degenerate d orbitals of metal ion into 2 sets of d orbital of different energies under the influence of approaching ligand is called crystal field splitting. Okay, the splitting of 5 degenerated d orbitals into 2 sets. Okay, dxy, dyz, dxz and dx square minus y square and dz square. 2 sets will be arranged, that will be called as crystal field splitting. The extent to which energies of the 2 sets of orbitals are split in is called crystal field splitting energy. The 3 orbitals, that is dxy, dyz, dxz are directed between the axes are called T2G orbital. Directed between the axes are called T2G orbital. dx square, y square and dz square orbitals which point towards the axis are called EG orbital. Okay. The ligand which causes greater crystal field splitting are termed as strong field ligands. The ligand which causes greater crystal field splitting are called strong field ligands, while those causes lesser crystal field splitting are called weak field ligand. These 3 points are very much important. The pattern of splitting depends upon the nature of the crystal field. Crystal field splitting in octahedral coordination entities, crystal field splitting in tetrahedral coordination entities. Okay, these are the 2 pattern of splittings. Crystal field splitting in octahedral coordination entities. In an octahedral complex, 6 ligands surrounded central metal atom ion, there will be repulsion between the electrons in metal, d orbitals and electrons of the ligands. In an octahedral complex, 6 ligands will be surrounded by metal and there is a repulsion between metal and ligand. dx square and dz square orbitals are directed along the direction of ligands and experience more repulsion. Those 2 orbitals which are dx square minus y square and dz square orbitals are directed along the direction of ligand, so it will have the repulsion more and they have more energy also. Remaining dxy, dyz and dzx orbitals are directed between the axes of attacking ligands, experience less repulsion by the ligands, they have lesser energy. These 3 will move between the axis, that's why it feels less repulsion and it has less energy, but these 2 ligands or these 2 orbitals will move towards the direction of ligands, that's why it has more repulsion and more energy. The energy separation between two split sets is denoted as delta naught. The energy of the Eg orbitals increases by 3 by 5 delta naught and that of T2g orbitals decreases by 2 by 5 delta naught. This is overall octahedral coordination entity. See here, octahedral, how dx square minus y square and dz square, okay. It is having 3 by 5 delta naught here, remaining dy xy, dxz, dyz having 2 by 5 delta naught. Average energy of the orbitals in spherical crystal field, and this is overall octahedral crystal field, okay. Here energy will be getting raised. The crystal field splitting delta naught depends upon the field produced by the ligand and charge on the metal ion. Some ligands are able to produce strong fields, in which case the splitting will be large, whereas others produce weak fields and consequently result in small splitting of the d orbital. Next, crystal field splitting in tetrahedral coordination entities. In tetrahedral complexes, 4 ligands may be imagined to occupy the alternate corners of the cube and metal ion at the central of the cube. How? You can expect 4 at the corners and 1 will be the center metal atom. Energy of T2g set of orbitals is greater than energy of Eg set of orbitals. In such complexes, d orbital splitting is inverted and it is smaller as compared to the octahedral field splitting. Then the crystal field splitting will be inverted in tetrahedral according to octahedral, okay. So dxy, dxz, dyz, which is T2g level, has less energy, that is 2 by 5 delta naught. Here 3 by 5 Eg levels will be having 3 by 5 energy splitting. Orbital splitting energies are so low that pairing of electrons are not possible. So there are high spin complexes. Here electron pairing will not happen because of high spin complexes. For the same metal, the same ligands and metal ligand distances, it can be shown. Delta T equal to 4 by 9 delta naught. For same metal, same ligands and metal ligand, how much energy will be present. Next, spectrochemical series. The arrangement of ligands in the order of increasing field strength is called spectrochemical series. The arrangement of ligands in the order of increasing field strength, we'll call it as spectrochemical series. Ligands are arranged in a series in the increasing order of the field strength. Okay, these are all ligands. They have arranged in the increasing field strength manner. Least is iodine, next bromine, thiocyanate, chlorine, sulfate, fluorine, hydroxyl, chromate, water, thiocyanate, okay, EDTA, ammonia, ethane 1,2, diene, and this is cyanate and carbonyls. Okay, this is about how ligands are arranged in a series in the increasing order of its field strength. Electrons in the d orbitals of metal ions, octahedral coordination compounds. Okay. In D1, D2, D3 coordination entities, d electrons occupy the T2g orbitals singly according with Hund's rule. Means the electrons in the D1, D2, D3 coordination entities, it will occupy the entities with singly occupation like Hund's rule. For D4 ions, two possible patterns of electron distribution arise. The fourth electron cloud either enter the T2g level or pair with an existing electron. In D4 level, what will happen? It will enter to the either next fourth electron cloud or enter to the same electron level. Okay. This depends on delta naught and pairing energy. The two options are, if delta naught is less than pairing energy, the fourth electron enters one of the Eg orbitals, giving the configuration T2g 3 Eg1. Ligands for which delta naught is less than P are known as weak field ligands and form high spin complexes. If delta naught is less than pairing energy, the fourth electron will enter to the Eg orbital and it is having configuration T2g3 Eg1. It will form weak field ligands and those weak field ligands have high spin complexes. In the other contrasting case, if delta naught is greater than pairing energy, it becomes more energetically favorable for the fourth electron to occupy T2G orbital with configuration T2G4 and EG0. Ligands which produce here known as strong field ligands to form low spin complexes. These are the two cases which you have to understand, in which the D4 electrons, where it will occupy. If it occupy, what configuration, what kind of complexes will be seen. Color in coordination compounds. When white light passes through a solution of transition metal complex, the solution absorbs certain electromagnetic radiations of white light. The color of the complex is complementary to that which is absorbed. Means whatever the color has been absorbed through a solution of transition metal solution, the color will be given out whatever the complementary color has been absorbed. If it is orange color, absorbed color, here observed color was blue, and the opposite range whatever you are seeing, something will be observed and another way of coloring will be observed. Okay, this is due to absorption, this is due to what we are observing. Example, the complex of titanium complex which is violet in color. This is an octahedral complex where the single electron in the metal of d orbital in the T2G level in the ground state of the complex. The next higher state available for the electron is the empty Eg level. Means in the titanium only one electron is present in d level, d orbital in the T2G level, that is in the ground stage. The next higher stage is empty in Eg level. If light corresponding to the energy of yellow-green region is absorbed by the complex, it would exit the electron from T2G level to Eg level. Consequently, the complex appears violet in color. It is having only one electron. When the light has been produced over that complex, it will raise to the or it will jump to the next Eg orbital level and it will give from yellow-green color to violet in color. The crystal field theory attributes the color of the coordination compounds to D transition of the electron. Why it has been colored? Because of DD transition of the electron. This question may ask in your competitive examinations as well or your board examinations also. This titanium complex which is having only one unpaired electron in the T2G level, how it become violet means, how it become colored means due to the DD transition of the electron which happened through crystal field theory. Influence of the ligand. See, this is how you can observe from white light how that yellow-green color can be turned into blue. This is titanium complex which is having violet in color after the absorption of light. Influence of the ligand on the color. The absence of ligand, crystal field splitting does not occur and hence the substance is colorless. When ligand is only not present in the complex, obviously the crystal field splitting will not occur, so that overall complex will become colorless. Removal of water from this titanium complex on heating renders it colorless. Similarly, anhydrous copper sulfate is white, but copper sulfate pentahydrate is blue in color. Normal copper sulfate is white. When the ligand is added like water, it will become blue in color. Okay, another example, nickel hexahydrate complex which forms when nickel chloride is dissolved in water. If didentate ligand ethane 1,2 diamine is progressively added in the molar ratios 1:1, 2:1 and 3:1, the following series of reactions and their associated color changes can be occurred. See here, first will be green. When ethane 1,2 diamine is added, pale blue will be formed. Okay, for that again progressively that diamine is keep on adding, blue or purple will form. Next, still the progressive addition is there, then it will form violet color. Okay, first it will be green, next pale blue, next blue or purple, later it will form violet color. Here it is proving that due to the presence of ligand, you can, if you add progressively with molar ratios to the complex, it will change color from one changes to another color. This is the influence of the ligand on the color. Next, limitations of the crystal field theory. The crystal field model is successful in explaining the formation, structures, color and magnetic properties of coordination compounds to a large extent. However, it has certain limitations. Crystal field theory assumes that the ligands are point charges. It follows that anionic ligands should exert the greatest splitting effect. But anionic ligands are found at low end of the spectrochemical series. Okay. From the crystal field theory, we have successful explaining in the formation, color formations, structures and magnetic properties. They are telling like ligands are point charges in the anionic species will exert the greatest splitting effect. But in the spectrochemical series, anionic ligands are found at the lower end of spectrochemical series. It does not take into account the covalent character of bonding between the ligand and the central metal atom. It does not take into any account between the bonding in central metal and ligand. It cannot explain the color of the substances with full or empty d orbitals. It will not explain the complexes with having complete d orbitals or completely empty d orbitals. So these are the limitations of crystal field splitting. Next, bonding in metal carbonyls. The homoleptic carbonyls compounds contain carbonyl ligands only, like this metal atom with carbonyl, that is metal carbonyls, are formed by transition metals. Metal carbonyls will be formed through transition metals. Nickel tetracarbonyl is tetrahedral. Iron pentacarbonyl is trigonal bipyramidal. Chromium hexacarbonyl is octahedral. Manganese decacarbonyl is made up of 2 square pyramidal. And cobalt octacarbonyl has a cobalt and cobalt bond bridged by 2 carbonyl groups. Means here homoleptic carbonyls are present, means all the side only carbonyl ligands are present. Okay, these are the some of the carbonyls. Example, this is tetrahedral in nature, this is trigonal bipyramidal, that is octahedral, this one is square pyramidal and this one bridged carbonyl group you may see. Bonding in metal carbonyl, here you may observe about synergetic bonding. The metal carbon bonds in metal carbonyls have both sigma and pi characters. See here sigma and pi characters you may observe. Okay. All sigma bond and sigma bond is formed when the carbonyl carbon donates a lone pair of electrons to the vacant d orbital. That sigma bond is formed when the carbonyl carbon donates a lone pair of electrons to the vacant d orbital of the metal. This sigma bond will be come from carbonyl to metal for the completeness of, to complete that vacant d orbital. A pi bond is formed by the donation of a pair of electrons from the filled metal d orbital to the vacant antibonding pi star orbital. That pi will be form pi star antibonding orbital, also known as back bonding of the carbonyl group. First sigma bond will form by donating electron. Here pi will form, that will be given out the electrons to the pi star, which is anti-bonding, to form anti-bonding orbital, and that can be called it as back bonding of the carbonyl. Thus a synergetic effect is created due to this metal to ligand bonding. This synergetic effect strengthens the bond between carbonyl and the metal. Sometimes this will give and it will back giving to the carbonyl, so it will create the synergetic effect, and that's why the effect strengthens the bond between carbonyl and the metal. This is how bonding between metal and carbonyls will form. Stability of coordination compounds. The stability of complex in a solution refers to the degree of association between the two species involved in the state of equilibrium. Stability can be expressed quantitatively in terms of stability constant or formation constant. Okay, metal with 4 ligand, it will form metal with metal ligand complex. Overall stability of constant will be beta, concentration of metal complex divided by concentration of metal plus concentration of ligand. For this reaction, the greater the value of stability constant, the greater is the proportion of metal ligand complex in the solution. This point is very much important. Greater the value of stability constant, greater is the proportion of metal ligand complex. Free metal ions rarely exist in the solution, so that metal will usually be surrounded by solvent molecules which will compete with the ligand molecules L and be successively replaced by them as follows. See here, when metal and ligand, it will be having K1, Ml plus L, Ml2, will be represented as K2, Ml3, Ml2 plus L, Ml3, Ml3 plus L, Ml4, K1, K2, etc. referred as stepwise stability constants. Alternatively, we can write that overall stability constant as beta 4 also. Beta 4 equal to K1 into K2 into K3 into K4 or more generally, and beta n will be K1 to Kn. The reciprocal of the formation constant is called instability constant or dissociation constant. The reciprocal or the inversion of that formation constant is called instability or dissociation constant. Okay. Applications of coordination compounds. In many qualitative and quantitative chemical analysis, color reactions are given by metal ions with a number of ligands, especially chelating ligands, which help in the detection and estimation. Hardness of water can be estimated by simple titration with sodium EDTA, which forms stable complexes with calcium and magnesium ions. Articles can be electroplated with silver and gold much more smoothly and evenly from solutions of the complexes like silver cyanate and gold cyanate than from the solution of simple metal ions. It is used in qualitative and quantitative chemical analysis and estimation, hard water estimation. Next, electroplating. Some important extraction process of metals such as gold and silver make use of complex formation. Next, coordination compounds are used as catalyst in Wilkinson catalyst for the dehydrogenation of alkenes, rhodium chloride. Chelate therapy is used for the medicinal chemistry. For example, EDTA is used in the treatment of lead poisoning. Some coordination compounds such as cisplatin and related compounds inhibit the growth of tumors. Okay. Coordination compounds are of great importance in biological systems. For example, chlorophyll is a coordination compound of magnesium, hemoglobin is a coordination compound of iron, and vitamin B12 is a coordination compound of cobalt. Okay. Here you can observe through biologically also applications are there, and in so many processes it will be used as catalyst, and for inhibit the growth of tumors also coordination compounds are being used. And this is about the overall coordination compounds with its properties. I hope you have completely understood whatever I have taught about the coordination compound. So, we'll meet in the upcoming new chapter. Till that, thank you.